With Karl's contribution, and we'll, I guess, probably try to break for lunch around 12:20.
Let's say I come as far as I come, okay? Because what I want to do is this one. This one. How did you pick?
I think it's the other.
It's this one, that's why.
Okay. It was a nice trick, thank you. Okay. What I wanted to do, I wanted to give you examples in quantum electrodynamics in 1+1 and 2+1 dimensions. If there is time, I can also show you how we do real-time evolution with quantum computations. And I guess I wanted to give you an introduction to our center, but this is not so important. I wanted to start with the Schwinger model. What is the Schwinger model? It is one space, one time dimension. If we go to the Hamiltonian, we only have one space dimension, and we have the Hamiltonian, and what you have is a kinetic term with a gauge covariant derivative. You have a mass term, and you have the electric field, the time derivative of the gauge potential, and you have a constant external electric field, which is given here by this parameter theta. And this model is interesting for us for quantum computation because it has a phase diagram where you plot the mass divided by the Baer coupling, and then you have, if this is larger than 0.33, roughly 0.33, then you have a first order phase transition at a certain value of theta, and if you have it in units of 2 pi, which is at a half. Such a situation with an external electric field is extremely difficult for Markov chain or Monte Carlo simulations. They could not explore the phase diagram if you have Monte Carlo methods. And therefore, it's a nice example to do it with quantum computations, which is based on the Hamiltonian, which doesn't have this problem of Monte Carlo. So the first step is to discretize this Hamiltonian. So, and for this you have this nearest neighbor interaction. So you have lattice points n and n+1. This u is e to the I times the gauge potential. It's the parallel transporter that we normally use in lattice gauge theory. And you see we have again the kinetic term, nearest neighbor interaction with the parallel transporter. We have a mass term. This 1/a comes from a particular way of discretizing. It's a so-called mass shift. It's not so important for the talk here. And we have also this external electric field where this L0 is theta over 2 pi. And we have a mass shift. I was hoping that Igor would be here because he has calculated this mass shift. This is why I put it here.
Sorry, one question.
Sure.
The mass shift we have is when a goes to 0, like the difference is sub-leading. This is 1/a.
Yeah.
So this blows up in the continuum limit.
Exactly. So you have to renormalize the mass. You have to determine the mass shift such that you compensate this 1/a term.
Okay. In our choice, in our paper, we didn't have this 1/a, and then the mass shift was just some term that goes with a. Now this 1/a I'm not familiar with, but then your lattice mass will need to have a minus 1/a.
This is Wilson fermions. Okay.
Oh, sorry?
This is Wilson fermions.
Okay, that's the difference.
I come to Steggert.
Yes, sorry.
This is Wilson fermions, but it has also this generic mass shift that you have to compensate. So this is the discretized version, and now you have to do something that Alice called encoding. How can I make this available for a quantum computer? And this goes through the Jordan-Wigner transformation, and through this Jordan-Wigner transformation, you can express this operator or this Hamiltonian in terms of Pauli matrices. So these x and y's, they are Pauli matrices. This all looks pretty complicated, but you can write it down explicitly. So you have, again, this represents the kinetic part. It has a parameter x that I ask you to remember. X is 1/a, essentially. So if you send x to infinity, you send the lattice spacing to 0 and you get the continuum limit. This is the remnant of the mass term after this Jordan-Wigner transformation, and this is the remnant of this external electric field. The message here is, we don't go through the derivation, the message is what you can do, you can express the Hamiltonian of the previous slide in terms of Pauli matrices. And when we have this in terms of Pauli matrices, we are at the Ising model essentially, we can teach this to a quantum computer. And you see also here we have X gates or X operators, so we also have to do this post-processing, this going to the Z basis, to the computational basis. And then we have operators that are also expressed in terms of Pauli matrices. This is the electric field density operator. And you can also define the particle number operator, all in terms of Pauli matrices. Which means when you have the state at the end of the quantum circuit, you can measure this operator and you get a value. And you have to repeat these measurements many, many times to get expectation values. This is the same for the Schwinger model with staggered fermions. Again, you have a kinetic term, you have a mass term, and you have this electric field. It also has a mass shift, which was computed by this gentleman over there and in the group. You can again transform this through the Jordan-Wigner transformation in terms of Pauli operators. So you can bring this immediately to a quantum computer. Okay. This is how we determined this mass shift. We measured the electric field density divided by the Baer coupling. And what this formula tells you, this is a mass perturbation theory, is that when the mass is zero, then this electric field density should vanish. This is all proportional to the mass. So therefore, when we measure this, and this is our largest volume, this is our largest volume, when this is zero, then we can read off what is actually the mass on the lattice that corresponds to a zero mass in the continuum. And we can do this both for Wilson and for Stecker. And we checked that indeed, if we are on a large enough lattice, then we find this predicted behavior from your paper. So we checked this all comes out very nicely. Then you take your qubit Hamiltonian with this Pauli matrices, and you have an ansatz. The ansatz is your choice of the quantum circuit, and then you do what Alice explained to you. You measure this expectation value on the quantum computer, which brings you down from an exponentially hard problem to a polynomial problem, because this the quantum circuit only scales polynomially. You put this expectation value and the parameters to these classical optimizers, and then you repeat this. Just to explain again what Alice has already explained. Sometimes it's good. And you see, we thought a lot about the ansatz, the quantum circuit, and this is not just a generic efficient SU2 that Alice showed, but we have SO4 gates, which can be recomposed into these elementary gates. This was your question, that we really can construct very complicated gates, like SO4 symmetric ones, but there is a way to recompose this into elementary gates. And also the quantum structure, the quantum circuit structure can be very different. So for example, here we have generic gates like an SU4, or we also tried SU4, and you can have like a brick structure, or you can have a ladder structure, and you have to try all this to see which of these circuits works best for you. So there's a lot of thinking, understanding the physics of the model to come up with choosing this gate to be an SU4 and having either this brick or this ladder structure. And here comes something, what you have to do. The results are really noisy, and when you do a simulation, then if this is the exact value, you often find that the quantum computer gives you a value of this for some observable, let's say the ground state energy, and you're really pretty far away. But then you can play a very simple trick. So this error here comes from the noise. But what you can do is you can increase the noise. You can add more gates in your circuits, like a C0 before the gate and a C0 after the gate. A C0 times a C0 is a unit matrix. So it should not do anything but increasing the noise. And then you can increase the noise many, many times. And then what you see, hopefully, is this figure here. Namely, you can do a linear extrapolation and you find the mitigated value of the observable that you want to have.
But will it always be linear? So the amplified values, will they always align?
When it works, then it is linear, and it is aligned, and you can nicely extrapolate. When it is not linear, yeah, you do not get it. So it was actually up to us that we forced, so this is something that is built in IBM, in Qiskit, the programming language that is used there. We forced IBM with our group that they make this data available, also the error of the data, such that we can do our own extrapolation and that we do not blindly linearly extrapolate, but like in this case, we have to do a quadratic or whatever. Okay, so sometimes it works, sometimes it doesn't work so well. Thanks for the question, I was prepared.
And so is it understood when will it work, when it will not?
No, it's not. No, it's not. That's a big problem. It also, depending on the model that you want to study, it depends on the observable. There's some theoretical understanding missing, and therefore I think this zero noise extrapolation at the moment is the method of choice, yes, but people are thinking of much more elaborate error mitigation schemes. But I wanted to show you something that is used today.
Is it clear that it's even monotonic? Like, couldn't you sometimes undershoot the expectation value, sometimes overshoot?
You do. It really, especially if you put too much noise, then the value becomes erratic, and you do not know. So you have to find an interval where it makes sense to extrapolate.
How do you quantify the noise? Like, say, double the noise. What is the quantity?
We only have noise levels. So we start with the first noise level, 2 C0s. Then we add 2 other C0s, and so on and so on. And we have these noise levels. That's the only information we have. You could estimate from the calibration of the machine how large this noise could be, but this changes every day. These machines are calibrated every day, and it's the art. You have to know when is the calibration, because then the probabilities that there is a noise is exact, or you know it very well. If you wait 2-3 hours, then...
So this 1, 2, 3 is like adding layers to your circuit or something like this?
Yeah, exactly. So you choose an RX gate and you make a C0 before, after. Then you have another RX gate, you make a C0 before and after, and so on. Okay, but then you are there. So you explore the phase diagram. So I show the phase diagram here again. And in this simulation, we were running down here, so you should not see any sharp transition. And indeed, what we did, this line here is essentially mass perturbation theory. Then we used staggered fermions, we used Wilson fermions, we used exact simulations, and we used really hardware runs. And what you see is that you do not see anything. And this is very good, because this means that in this case, our hardware runs really reproduce the exact simulation, the analytic mass perturbation theory, and the hardware data. This was a very nice example, but I have to say, we went really here, so we went really far away from the phase transition. We did also the same, going to a mass that is very large, so we are somewhere up here, and there we should see this first order phase transition, and then for 3, 4, 5, and 6 qubits, you see it in the electric field density and also in the particle number, that roughly at the expected value of this theta, this constant external electric field, you see a sharp first order transition. Okay, so this was very nice. Again, this was done as before with exact simulation and also with hardware. And again, you see that you don't see anything. So also in this case, it works. Here comes just 1 second, then I get your question. One disclaimer, we really had to go to these extreme cases to see the effect. We tried to go closer to the phase transition, and this is all washed out. The noise was too large that we could identify this phase transition. I take your
I think you
question.
just answered. My question was going to be if you can extract any information about the critical point, but I assume you cannot because you cannot get close.
You cannot get closer. It's unfortunately, I mean, you can do it with matrix product states, but not in the quantum computer. Yeah. Sorry. Any other question concerning the Schwinger model in 1+1 dimension? No? Okay. Then, let's be brave, let's be ambitious, let's go to 2+1 dimension. The Hamiltonian doesn't look so easy anymore. Again, you have a kinetic term. You have another kinetic term. This is staggered fermions. So here you have a phase vector. You have the mass term. You have the electric part. So this is the electric field operator. And the new effect is that you also have a magnetic part. So this is the plaquette operator. So this is your lattice. These are the staggered fermions. This is your plaquette operators. These are these parallel transporters that go around this plaquette. And that's now your Hamiltonian.
There's no Chern-Simons or anything that it's not. You cannot add the Chern-Simons here.
I think yesterday I had a meeting with my group who is studying the Chern-Simons term. I think after 4 years of thinking how this should look like in 2+1 QED, we know. So we are just about writing up a paper to propose what can you do with a Chern-Simons term in 2+1 dimensional QED in the Hamiltonian formulation. And Hamiltonian formulation means that you can study 2+1 dimensional QED with Chern-Simons term on the lattice. But this is really work, I would say, very much in progress. And I just wanted to show that already in such a complicated model, we can do some quantum simulation. This is still simulation. We can compute particle masses, really particle masses in 2+1 dimensional QED. So this is a particle mass as a function of the Baire coupling. And this is for different discretizations of U1. But we can do this now. We are in the stage that we can really compute the spectrum in generic quantum field theories, also when we have plaquette terms, which I find very nice.
A question on this. You still have fermion doubling problem on this. Do you still have fermion doubling problem?
No, staggered fermions.
In 2+1 dimension, don't you need the plaquette to be 4 sides, 2x2? I don't know 2+1 dimension.
How many fermions are there in the continuum limit? Maybe that's the question.
This is 2 flavors. So we will get
Perfect.
this is the 2-flavor formulation. You can also have a 1-flavor formulation when you have the 4-dimensional gamma matrices. But here we have the sigma matrices. So this is 2-flavor theory. Okay. If this was the question. And again, you see, I mean, the basic building block of the quantum circuit looks like this. This is really well tailored to, for example, conserve the charge in the theory. If you use this building block for your quantum circuit, then your charge is conserved. Okay. But again, this took really a lot of time to come up with this structure.
So just to check, so for 2+1 dimensional theory, is it more convenient to also have a topology of a quantum computer, which is more like in a plane, or that?
Yeah. I mean, to bring this model on an IBM quantum computer will be difficult because an IBM quantum computer has a structure. Basically, it has this hexagonal structure, so some rings like this, and they are put next to each other. And you have also nearest neighbor interaction in both directions. So if you want to have an interaction with the qubit there, you have to do a number of swap operations to come there. And every swap operation, Alit, you mentioned this, a swap can be decomposed in C-naughts and rotation gates. There are many, and each of these gates produce noise for you. So for this problem, we're actually looking for a different hardware. And I will not tell you which one. You will find out. Okay. So good. Yeah, sorry.
So this plot again. So I should read the extrapolation to the left, right? So the continuum extrapolation moving right to left.
Beta should go to the left, yes.
And then so
No, sorry, beta should go to the right. Beta is 1 over g square, and g square should go to 0. So beta should go to infinity.
and that's the gap. So that's the gap. So I mean, like just what should I read the result in this plot? So this is these two lines. This is two different particles.
No, these are, you cannot put U1 directly on the quantum computer, right? Because it's a continuous variable. So you have to discretize it. And we discretize it with Zn. Okay, actually with Z2L plus 1. So if I write here a discretization of L equal 1, I have Z3. If I have L equal 2, I have Z5. And here I have Z7. And we try to see which discretization can I allow myself in order to converge. And what we see is that with L equals 3, it seems to be good enough to be close enough to U1. Okay.
And then that would be the gap in units of.
Here it is the gap in lattice units, so dimensionless. It's a number. You cannot give it in physical units. I can make an advertisement. This is something we did to compute the running coupling in 2 plus 1 dimensional QED. It's a paper that just came out last week. And what we do on the quantum computer is computing something that is called step scaling function. Is essentially the running of the coupling. And what we can do on the quantum computer is to go to beta values of about 90, which would be completely impossible with Monte Carlo. So we can really reach extremely small values of the coupling, which means in principle we can make contact to only one loop perturbation theory, which would allow us to compute the lambda parameter, right? In order to get a physical value of this, we need as an input the physical value of the lattice spacing. And for this, we are doing Monte Carlo simulations that give us the value of the lattice spacing at this point here, and then through this step scaling procedure, we can filter it through to all the beta values that we have. It would be a talk by itself, but I just wanted to show you that I have in mind that we, at the moment, can combine quantum computing with Monte Carlo simulations to really extract quantities in physical units. But what I wanted to discuss here, because this also relates to other talks, is the static potential. So in 2 plus 1 dimensional QED, the static potential has a constant term, then it has a Coulomb part, which is a logarithm in 2 dimensions, and then it has a linear part. And when you plot this potential, and you have meta fields, then you have, for small values of g, you have the Coulomb part, the logarithm, then you have a linear part from this term, and then you have string breaking, which means that the potential becomes flat. Okay. And what we do here, we keep our distances in the static potential, this r, in lattice units constant. So only, let's say, only 3 lattice points. Okay. And then we vary g. We make g smaller and smaller, or larger and larger. And when we make g smaller and smaller, so g is decreasing, then also the lattice spacing decreases. And since the physical distance is given by the lattice spacings times the distance in lattice units, so r physical is a times r, and r is 3 lattice points, we can simply vary the value of g to get to different physical distances. Is that clear? Was it clear? Okay. Okay. And what we do here, oh, the colors are coming off. This is nice. We are aiming here really at the quantum computation of the system and exploring the static potential. So therefore, we are using only small system sizes, like a 3 by 3 or 4 by 4 open boundary condition system. And we are aiming at larger systems in the future. If you have such a situation, you can have a static potential, and here the colors are really missing, where you have static charges like here and here. So you have a distance of 1, or here and here. You have a distance of square root of 2, or here and here, or here and here. And we exploring all these distances, and we are trying to get the potential, the static potential in the different regions. And what I want to show here is, so for example, we go to such a value of G, which means that we are in the Coulomb part of the potential. And what we can do now, we can really plot the electric field fluxes in the system. And you see, the static charges are here. And if I'm in the Coulomb part, then I have electric fluxes like here. So there's a 1. So these are dynamically generated. Or we have fluxes like basically all over the lattice, like here or here, which means that if I'm in the Coulomb part and I plot the electric fluxes of the system, I basically have a Coulomb behavior. I really have this flux that goes all over the lattice. You are shaking your head.
I'm just thinking. It's okay, I'm just thinking about processing.
You need time to process, or it's okay. If I go to the linear part, so I go to this value of G here, then I see I basically have a confinement string here. So there are the static charges, and here's electric flux. And I can really see with this electric flux picture that this confinement string is building up. And I can also see if I make more experiments that I do not only have this strict confinement flux here, but that I also have fluctuations. So the flux can also go around here, which, if the system would be much larger, I could really explore the properties of this confinement string and really say what is the width of the string, how is the density of the string, and all this. I can really explore this by evaluating these electric fluxes on the lattice. This is now, I would say, a proof of principle or a benchmark, because we want to bring it on these NISC devices, but we can do this. Yeah, and then I can also go to this here, and what I see, I don't have any flux anymore, nowhere on the lattice, so the string is really broken, and what I only have is at these points a heavy light mesons. So this is really the picture that I can represent or visualize of what is happening in the static potential, and the same would be true, of course, in QCD. Now 2 questions. Time is basically over. You have questions to this QED part?
I might be a little bit technical. So in the Schwinger model, the advantage of the quantum computer was solving a sign problem, right? In 2+1D QED, what is exactly I mean, you mentioned that you can go to very finer lattice spacing, but what exactly causes this advantage?
So in this case, the answer is twofold. First of all, we wanted to find really the fundamental formulation of the Hamiltonian, the circuit for quantum electrodynamics. Okay, and we wanted to have one application. The application is to really determine a physical quantity, the lambda parameter, the non-perturbative lambda parameter. And for this, I can go to very small values of the lattice spacing, meaning to very small couplings, and only need a one-loop calculation. I have done this myself. There are different ways of computing the running and so on, but this would be an application. The second answer is this is now the fundamental formulation, for example, adding a Chern-Simons term, or adding a non-zero matter density, or perform real-time evolutions. Okay. But this took us 3 years to come up with a setup where we have the Hamiltonian, the qubit Hamiltonian, where we have good circuits, where we have good Ansätze, where we have good initial points, and where we have good classical optimizer to put this all into equilibrium. I think I don't have time to I just show you the picture. So this is, for example, a quantum circuit for real-time evolution. So in this block here, there is a quantum circuit that is extremely large, has a very large number of layers, and this represents the time evolution. You see all the stuff here, what we had to do to make a time evolution of 1+1 dimensional Thirring model.
Why does it have this structures? Because of like light cone?
Yeah, it's basically the light cone. So we want to scatter wave packets. So we generate a wave packet here, and it's localized on these qubits. So we don't need these qubits here. So we started with filling this completely up, but then we realized we don't need these qubits, and only when the wave packet travels in this direction, we have to add more and more gates. So we could save almost half of the gates that would have generated noise. And the same is true here. So here, the wave packet scattered. So if I follow only one wave packet, again, I don't need these qubits. Okay, so
why are only following one wave packet? Not where is the second?
The second would come in addition. Okay, I just wanted to show you part of the, not to shock you too much. And what we did is, so we did this with an exact simulation, and then on the quantum hardware, we took time slices. So maybe I show you this. No, sorry, I'm going in the wrong direction. I will skip all this. Don't worry. And this is what you see with the scattering. Okay, so you have one wave packet here, one wave packet there, and then you see that there's a repulsive force. And we wanted to reproduce this on the quantum hardware. So we had to go to even less qubits, and we made time slices. And in these time slices, for example, here, so I have forgotten which one is the exact simulation and which one is the hardware result, but you see again that you find a very good agreement between hardware results and exact simulation. Okay, with this, I skip all this. I can just tell you, no, I skip it. I don't skip the group. So we are at the moment like 22 people, and I'm very proud. This is 50% female participation and 50% male participation. 3 females are missing here on the picture. We started with 2 PhD students in 2020. Now we are at 22 people. Let's skip this. I want to point you to something Andreas is very much interested in, and now even contributing. In last year, in October, we had a quantum music symposium in Berlin. So these are more than 30 people who are working on quantum music. We have now already 3 publications about it. If you're interested, talk to Andreas or me. So my summary would be that at the moment what we are really doing first quantum computations for lattice gate series on the order of 10 to 20 qubits on these devices. But we are now, and we're doing this in 1 and 2 plus 1 dimensional QED, for example. We can address topological terms and non-zero matter density. We can do real-time evolution like scattering processes. There are many proposals for non-abelian gate series, and I will be curious which one will be the winner. And we are also performing really essential algorithmic and methodological developments to make quantum algorithms better. We are now entering the area where we really can do demonstrations, and demonstrations mean that we can really use 100 qubits, and that we can go to a depth of the quantum circuits of order of 100. Which would correspond to 3,000 to 5,000 CNOTs, which was unthinkable, let's say, 2 years ago. And this would really allow us to go to realistic sizes, even to go to 3 plus 1 dimensions, and then we can start to challenge these tensor networks, because they are also in the Hamiltonian formulation. They can also do the sign problem, real-time evolution, and all this. And I think after this area, we can really say, where can we achieve the quantum advantage for what and when. And of course, in the future, we will have fault-tolerant quantum computing, and I all encourage you to read our book about quantum computer music. And with this, I thank you for your attention. We still have for a question?
Yeah, a question.
So you had one slide with Tirring that you passed by.
Yeah.
Was this Tirring in 1 plus 1 or in 2?
This was in 1 plus 1.
1 plus 1. Is there any way you could see the Tirring Sine-Gordon duality in this language?
No, in this we didn't look at this, but there is a group in Taiwan also working with a group at the Max Planck Institute in Munich, they have looked at all these questions and they have studied this duality, they have studied the phase diagram, and they really looked which point it belongs to what. So there's a very, very detailed study from a very good group who has looked exactly in this duality.
Okay, if people are hungrier than curious, well, thank you very much.